curious patchiness in the decoration with AMPP and P, right?
Yes.
Did you ever see them move in ATP patches?
We have seen something like this. It doesn't work. It's a shame. Actually,
Because they were quite large, right? The sort of areas of brightness.
yes, yes.
Certainly many waters.
I saw that a few days ago. Okay, this is an example. It's not the best one. It was it's very short. It was one of you see those patches.
That looks normal. I mean, there could be single molecules, or there's 2 or 3 at the same point.
Could be, and in addition, the problem we got is that we saw that only at very, very low ATP concentration, few micromolar. As soon as you increase the ATP concentration, every evidence of jump disappears suddenly. So probably we had an interaction of 1.5 kb.
Yeah.
So it's probably completely negligible when you have ATP. On the other hand, if you have some mutant that increases the interaction between side molecules, in that case it could be relevant. For instance, if you have sick cells or mutations, you can jam more easily the traffic.
Well, I was worried about maybe the microtubules being patchy in some way in your experiments, and decoration sort of reflecting either microtubules being covered up by polylysine or something that you would see in the control where they should move. Because if they move over the dark spots should be okay. But if they don't, then there's something wrong with the dark spots. That's what.
That's a possibility. That's also a possibility. We discussed it. We tried to find out the different ways to be sure not to put polylysine or other stuff, but we can't fight against the defects of the microtubule. You say that you have one defect per micron or less. So in principle,
depends on how you prepare them. And you had, I think, 30 micromolar Taxol. So the more Taxol you add, the more patchy they get.
okay.
And, you spin them and resuspend them, and you know, it's plenty of possibilities for things that would happen. I don't know, which is not good. Maybe one last question. For your perspectives, you were saying, or you also list the various things working on DNA, working on entire tissue, homeostasis and all that. Are you planning to discontinue all these single molecule experiments, and especially all this last technology that you have set up? Or you want to
yes,
broaden the operation?
I think that we are going to continue on single molecule on 2 different directions. One is the magnetic tweezers, because they are very fun experiments. So I like them, and they are rich. We can perform them as much as we want by changing the sequence, changing the protein, adding 2 factors. So it's a world. So I think we are going to improve the magnetic tweezers as much as we can. We start discussing with Jean-François and Vincent to see if we can combine our technologies to go farther and faster. And on the other way, I'd say that we're going to keep the experiments in vivo as a main direction. The collaboration with Maxime is very fruitful and interesting. Our own who made the experiments in Mysin 5 got hired by CNRS this year and continue other more complex systems like immune system and looking at single molecules in B cells, T cells. So I think we're going to continue in that way. And we have a new project on the drug delivery for cancer treatment with Francesca Farina and Marie Vitrex. And the idea is to use the single molecule approach to look at single drugs in the cell and see how the drug reaches the nucleus, how it enters the nucleus, and how the transport happens. I have a couple of slides about that because they are very recent results, but I like them. And, you try to take this kind of drug is based on DNA, small modified DNAs that are injected inside the cell. They reach the nucleus, and when combined with X-ray, they induce apoptosis in the cell. And because they are chemically modified, and the cell cannot undergo mitosis when it includes those fragments in the main genome. And the idea was first to see how they reach the nucleus. They had made some experiments directly in the cells, and we saw, without optimizing anything, we saw some directed motion, and after a few hours, you see that all those dots injected into the cell, when they are covered by a lot of DNA, they surround the nucleus. So and we suspect there is someone takes the dot and takes it to the nucleus. And so, for this reason, we are making experiments in vitro with the reconstructed, by mixing those DNAs, the quantum dots, and the intracellular medium to see if we form complexes. And we saw that, for instance, here, it's not very bright, but you see there is one microtubule, and you see that in absence of ATP, there are many spots on the microtubules. Some of them are fixed, others just diffuse a bit. And it doesn't happen when you don't have DNA. So the DNA recruits in some way some complex that takes it onto the microtubule. And recently, Francesca made the experiments. Made the experiments with ATP, and I don't know if you see the dot moving. We start seeing 2 or 3 moving dots per field of view, which means that there is some activity, some motor activity in the system. We don't know where it is from, if the complex includes one molecular model, or if the traffic along of the microtubules just pushes the DNA complexes or whatever. But I think it's a very I believe in this approach to have both in vitro and in vivo techniques to look at the same story. Because in vitro you control everything, you can reconstitute the extract, and in the cell you see the complexity.